Hello, everyone, and welcome back. In this series of the book reading session by the book AI and Machine Learning for Coders by Laurence Moroney, till now we have explored numerous numbers of techniques in NLP. We have explored convolutional neural networks for computer vision, did some research on images, data, and whatnot. But all of our data is some kind of a sequence or a series of data. If it's not an image, then we do convert the image into pixels that are again sequence of numbers as well. And what about some kind of stock prices? Like they go up and down, but they're in numbers. Similarly, some of the trends like Moore's law, which gets changed after every 2 years, right? So it predicts the number of transistors on a microchip that roughly double every 2 years. So for almost 50 years, it has proven to be accurate predictor of future of computing power and cost. So here's the graph for Moore's law and how it seems with density versus year. So as you can see, the Moore's law is a straight line while the density is kind of bulging up and down. The time series data is a set of values that are spaced over time. When plotted, the x-axis is usually temporal in nature. Often there are a number of values plotted on the time axis, such as in this example, there are a number of transistors in one plot and the predicted value of Moore's law in the other, right? So you can say that number of transistors is the density and the predictive value for Moore's law is the years, right? This is called a multivariate time series. If there's a single value, for example, volume of rainfall over time, it's called a univariate. So single value univariate, multiple values multivariate. With Moore's law, predictions are simple because there's a fixed and simple rule that allows us to roughly predict the future, a rule that has held for about 50 years. So, but what about a time series? So let's see in the figure here. So this is a real world time series, artificially created, of course, and has attributes of complex real world series like a stock chart or seasonal rainfall. So, despite the randomness, time series have some common attributes that are helpful for designing a ML model and to predict them. So, in this chapter, we'll be just going through these attributes and understanding what is time series all about. And then in the next chapter, we'll see how we can use ML to implement or to get values out of time series data. So as you can see in this time series graph, you can see that there are some values that are in a fixed block. So from 1000 to 1100, you can see there is the values are from 100 to 110, maximum is 120. So there is a kind of range for values. And then it goes directly upwards from 1100 and the value is 140. So 120 is the maximum for the previous one, while 140 and above is the highest for the next block. So there is some kind of attributes that we can figure out from the image itself. So the common attributes of time series, while time series might appear random and noisy, as you can see in the previous image, there are some common attributes. So let's understand them one by one. So first is trend. Time series typically move in a specific direction. So of course, as we, whenever we plot a graph, we always go from 0 to some infinity, to positive infinity or negative infinity. But we never start from plus infinity towards 0, right? So there is a kind of specific direction that we move into. In the case of Moore's law, it's easy to see that over the time, the values on y-axis increase and there's an upward trend. So in figure 9-2, we have seen that there is an upward trend. The values are It went once downwards in the block of 1200 time lapse, but then there's a specific trend that it's always going up, right? From the time of 1200 and above, it's tending to go upward. So there's kind of a trend for it. Of course, there won't be always the case. So as we have already seen, there was a downward trend, then there was an upward, then again downward, and finally the trend was going completely upwards. So that's the same case. We have to figure out the kind of direction or the kind of trend. Next is seasonality. Many times, series have a repeating pattern over time, with the repeats happening at regular intervals called seasons. So, what are seasons actually, and what do we understand by seasons? So, as we've taught as a toddler, we know seasons is changing of weather. So, it may be winter now, then it will be spring, autumn, and summer, and the cycle goes on. But the series of, or the time series that we're talking about here, when we talk about that, seasons is actually repeating pattern. So if you see a block of data having certain values in certain range, and then suddenly there is another block of values with different sort of range than the previous one, so we can be actually divide those two blocks into different values based upon the ranges. So that would be seasons. To understand that much better, let's see ahead. So consider temperature and weather. We typically have 4 seasons per year, with temperature being highest in summer. So if we plot the weather over a series of years, we see these peaks happening. So every 4 seasons giving us the concept of seasonality. So we see in the website traffic figure 9-3, this is actually a plot for traffic on a website, but we can actually see that it also shows a concept of seasonality, that whenever the curves are going up and down, so each up and down can be a one season and it's repeating itself, right? So the website traffic, what is plotted for figure 9-3, it is plotted week by week, and you can see regular dips. So you can see that there are regular dips. So why these kind of dips? So if there is a website, the traffic should be continuous or a straight line, or it should be either zero or a straight line that there is traffic. But why do we see such dips? So it might be the reason that this site is for software developers like us, and there are less traffics on weekends. So people don't like to visit these websites and work on weekends. So there is a slant dip there. Thus, the time series has a seasonality of 5 high days and 2 low days. So the middle one, as you can see, there is some kind of seasonal change where you can see that there is small peaks, not exactly accurate to the peaks in the left and the right. So we can see there must be some Christmas and New Year holidays roughly in the middle, and there adds another seasonality there, right? So this is the concept of seasonality. Then is autocorrelation. Another feature that you may see in time series is when there's a predictable behavior after an event. So there is a kind of predictable event that you can predict that this kind of data comes next after this, seeing the previous data, right? So there are clear spikes, but after each spike there is a deterministic delay called the autocorrelation. So let's see. So it's very clear that after each spike we see, so the data goes for 400 value, it's low, and then after it crosses 25 in time, it becomes, suddenly it goes too high, and then after, while it's reaching time frame of 50, it drops down exactly there. And this drop down, we can see it actually comes over a period of time. So there is a low, there is complete high, there is a deadly drop, then there is a low, some high, deadly drop, and the whole scenario goes on, right? So in this case, we can see that a particular set of behavior which is repeated. So autocorrelation may be hidden in a time series pattern, but they have inherent a predictability. So a time series containing many of them are predictable, right? So let's see what's the next attribute is. So next attribute is noise. So we already know that whenever there is some real world data, there would be some noise in it. There might be chances that the power of noise is more than the power of the real data, right? So we need some kind of data because in the real world, the model will inculcate some data while it's fed some input. So, as it is, the name suggests, noise is a set of seemingly random perturbations in a time series. These perturbations lead to high level of unpredictability and can mask trends, seasonal behaviors, and autocorrelation. So let's add some of the noise to our previous data, that was autocorrelated series, and you can see the noise that's added from time series 50, from time lapse of 50 to 200. There is some kind of change, that the highly deadly drop that we were experiencing earlier, it has some kind of vanished somewhere, right? So this kind of thing or autocorrelation becomes harder when we add noise to our data. So given these factors, let's explore how you can make predictions on time series that contain these attributes. So let's see the techniques for predicting time series. Before we get into ML-based prediction, the topic in the next few chapters, we'll explore some naive prediction methods, right? So these will enable you to establish a baseline that you can use to measure accuracy of your ML predictions. Naive predictions to create a baseline. The most basic method to predict a time series is to say that predicted value at time t plus 1 would be same as the value at time t, right? Effectively shifting the time series by a single period. So we would say that whatever I am doing right now would be the same thing that I'll be doing in the time now plus 1, right? So there is hardly any change in the behavior, what I'll be doing in a single period of time, right? So let's say there is a code next for plotting series. So we get in time, we get in series, and the format and starts from 0 and to none. So using plt.plot, that is functionality that we get from matplotlib. So before you write this down, do make sure that you have imported matplotlib. So we get the time, start and end, the series for start and end, and its format. Then we get the x label, that's time, y label, that's the value, and grid equals to, so we have a grid in our graph. Then for trend, we say time and slope equals 0. So we return slope into time. So if you have some problem there, let's go back to see what is trend. So trend was the first thing that we ever got here. So it's the direction, right? Trend is a directional in which upward or downward direction the values are moving. So the values or the upward downward direction is given by the slope. Hence, we multiply slope to time. Next is seasonal pattern. So we take the season type, time. Just an attribute pattern, you can change it if you wish, right? So it returns np.where season time if it's less than 0.4, np.cos, that's the cos function, season time into 2 into np.pi, and 1 divided by np.exponential of 3 into season time. So then we get the seasonality, time period, we take the time, we take the period, amplitude equals 1 and phase equals 0. So the season time, that is the seasonality. So in how much time the season or the phase it stays there. So it's time plus phase, percentage period and divided by period. So we return the amplitude multiplied by seasonal pattern of season time. Then noise, you know, noise is a random state. So we use np.random, random state of seed, and noise level equals 1. We input the time as well and we return rand n of time, length of time multiplied by the noise level. Then we have time, so we just need time, so we multiply 4 because we have 4 seasons multiplied by 365 plus 1 extra day, and D type float 32. We take the baseline as 10, series, trend, time, and 0.1, and baseline of 10, amplitude of 15, slope of 0.9, noise level of 6. And of course, if you don't understand this, we'll go through the text and we'll understand what's the whole code about, right? So we create a series, baseline plus trend of time comma slope, and add it to seasonality of time, period is 365, amplitude equals amplitude. So we update the noise of series plus equals noise of time, noise level, and seed of 42. So after plotting this, we'll get something like this. So if you don't understand the previous code as much, don't worry, it's just to create a random values and plot it on the graph. So it's a random seasonal values. So, and as you can see, there is some kind of seasonal change as well, right? So season goes up and then down, then season goes up, and a bit more up, then down. So there is a seasonal change there. So now we have the data, and now we can just split it into training set and validation as well as the test set, right? That we already know how to do it. So let's split the data into validation and training. So a good place to do this might be a time step of 1000, giving you training data up to step 1000 and validation up after the step 1000, right? So it says that, as you can see in the graph, for the time step of 1000 till that point, we take up the training data. So from 0 to 1000 is the training data, and from 1000 to the next, wherever the graph is going, we take the validation set, right? So let's just split it up. You don't actually need to do split here because you're just doing naive forecast where each value t is simply the value at the step t minus 1. But for purposes of illustration, in the next figures, we'll zoom in on the data from time step 1000 onwards. That is the validation data set, right? To predict the series from split time period onwards, where the period that you want to split from is in the variable split time, and use the code like naive forecast series split time -1 to -1. That is the opposite, right? So let's see that validation set and how it looks like. So this is the zoomed version of validation set. So it's pretty good. So we can see some kind of relation here that started over time. The predictions appear to closely match the original values, but how would we measure the accuracy here? That's the problem, because till date how we were doing the accuracy was we would use metrics accuracy, and we would just get the loss and we would see what's the validation loss, what's the training loss, or the accuracy for both, and then we would say if the model was overfitting or it's for predicting good. But how would we see that the accuracy or the losses in the time series step? So let's understand that next. Measuring the prediction accuracy. There are a number of ways to measure prediction accuracy, but we'll concentrate on two of them. That is mean squared error and mean absolute error. I'm sure that you must have done this in your high school or maybe in class 10th or 12th, and you'd be familiar with these concepts. But still, we'll understand it a bit for you. With MSc, you simply take the difference between the predicted and the actual value or at time t, you square it to remove the negatives, and you average it over all of them, right? So what's the meaning of mean squared error is you take the mean, that is subtraction, you square it, you take the square of the mean so that you don't get the negative values, and error to take the average of all, right? And simply for mean absolute error is you take the mean, that is predicted value minus actual value at time t, then you take the absolute of those to remove the negatives, and then instead of squaring, of course, and then you average over them, right? So How do we do that in Keras? Using Keras is we simply use keras.metrics.mean squared error or .mean absolute error and pass in the values, that is the X validation value and the naive forecast. And of course, any mathematical function needs numpy, so we have called the numpy as well. So the MSC turned out for the author to be 76.47 and MAE was 6.89. So as with any prediction, if you can reduce the error, you can increase the accuracy of your predictions. So we'll see how to do that next. That is using less naive, more moving average for predictions, right? So how we can decrease the value of the errors that we recently calculated. So in the previous naive predictions, we took the values at time t minus 1 to be forecasted value at time t. Using moving average is similar, but instead of taking the value from t minus 1, it takes a group values, say 30, averages them out and sets that to be a predicted value of time t. So instead of using the value of t minus 1 to predict t, we'll be using whole lot of like 30 average values before the time t to predict the value at time t. So here's a function for that which takes in series and window size. So it's actually a window for the number of series that we want to take as average. We'll take a window size. So we have a forecast and for time in range, length of series minus window size. So forecast dot append the series from time to time plus window size and we take the mean. Then we return an numpy array of forecast, right? So moving average would be moving average forecast, the function only, pass in the series, comma 30 and the split time minus 30 for till the end. So the plot figure would be of X size is 10, 6 and we plot the series of time validation with X validation and with the moving average. So let's see what the plot looks like. It's kind of fitting well, not exactly in the frame of 1100 time frame, but it's kind of doing a good job, right? So the MSc and MAE got 49 and 5.5 respectively. It did improve a bit, but this approach doesn't take into account the trend or the seasonality, so we may be able to improve it further with little analysis. So improving the moving averages. So we have seen that from the previous method that we were using, the moving averages analysis was pretty good, and now we are trying to improve it much better. Given that the seasonality in this time series is 365 days, you can smooth out the trend and seasonality using a technique called differencing. So, which just subtracts the value at t minus 365 from the value at t. So, this will flatten out the diagram. So, let's see how we are doing this. So, series at 365 like the last one, and we take the last number and we subtract it from the first one from the last one, right? So difference times become time of 365 till the end. You can now calculate a moving average of these values and add back in the past values. So we take the difference of moving averages and we pass in the different series and 50 with the split time, and also we have a function of difference moving average plus smooth underscore past, and then we pass it the same forecast, right, with different time series. So when we plot this, we already see an improvement in the predicted value. So here is it. So it's actually fitting it much better, and of course the MSc and MAE would go much down to show the clear improvement in the predictions. So in this chapter, we were introduced to time series data and some of the common attributes of time series. You created a synthetic time series and saw how you can start making a naive prediction on it. From these predictions, you established baseline measurements using mean squared error and mean average error. And it was a nice to take a small break from TensorFlow, but in the next chapter, we'll just jump back to TensorFlow and machine learning to see how we can improve these predictions. Meanwhile, let's just jump to Colab and see how our the project and the GitHub is working up and see the code. So in chapter 9, we looked into time series data and we had some nice predictions to create a baseline. So I am not running this currently, but I've done this before and you can see some of the plots that I got. So I hope there is no need to discuss this code again. You can just see my plots here, the time series plots, and how we have converted these, and finally how earlier what the whole thing was looking at, and the metrics, the mean absolute error was around 5.45, and then here is the loss after training the model. So I've actually trained the model using some SGD optimizers and 3 dense layers. Just that's the simple way to do it. So you can see how the losses are going down and suddenly it spikes up. Yeah, so this all will be understanding in chapter 9. So if you don't know, if you don't understood this, in chapter 10 actually we'll be going through these all. And yeah, you can see the mean absolute error went up, so it went to 8, and you can see the overfitting here as well. So we'll try to work upon these in chapter 10. Meanwhile, feel to just go through the code once in GitHub, and the link would be in the description. And do turn up for the next chapter 10, where we'll be understanding how to work with these time series data and apply it on ML, right? Thank you so much for joining in and keep learning.